All right. Hi.
Hey.
I guess some of you guys had an exam before?
Yeah.
How was it?
Good. Awesome. I don't know what to find out. It's
Fun. You guys like, must be sort of a mind shift going from manipulating Turing machines to manipulating real machines. But anyway, I think real machines are more interesting. But okay, so today we're gonna start dealing with the challenge of so last time, remember, we talked about how terrible it would be if we actually tried to allocate physical memory directly to processes. And we talked about all the different problems that would create, and it really seemed like a terrible idea. And then sort of we introduced this really nice abstraction of the address space that would provide all of these nice properties. But we really have no idea yet how we're going to provide this abstraction to processes. We know that we like it. We know that it sort of encompasses the types of things that we would like to be able to accomplish, but we don't know how to do it. So today we're going to start talking about how we actually do that, and specifically how we introduce a level of indirection into the memory interface in order to accomplish that, right? And we'll start talking about virtual addressing, which is the whole sort of really nice trick that makes this all work, all right? I just want to make a comment without much further explanation. The plagiarism policy in this class applies to everything you submit, right? Every time you submit code reading questions, scripts, whatever it is, the same plagiarism policy applies, okay? So just please keep that in mind. Okay. Any questions about address spaces? You guys remember address spaces? Remember address spaces? Monday? I know your brains are full of, what do you guys learn in 396? What is it?
The
pumping theorem. Yeah, there we go. The pumping lever. Oh, that's very exciting. All right, so with that all pumping through your brain, do you guys remember anything about address spaces? Remember, we came up with these 4 requirements for memory management. That these were sort of the goals of being able to multiplex this particular resource, right? So what is it? What do we refer to when we talk about granting memory? What does that mean?
Allocate the memory to the one who requests.
Yeah, I want to be able to actually give a process or task the ability to use memory, right? What about enforcing allocations? What does that refer to?
Ensure that the allocation takes place.
Yeah, that's part of the grant, yeah.
Prevent a process from accessing memory outside of process.
Right, so specifically I need to keep processes from using memory that's not assigned to them, right? If I don't grant you a piece of memory, I should be able to keep you from using it, right? What about reclaiming memory? What does that refer to? People have this trick of trying not to make eye contact with me, so I won't call them, but it's not going to work.
John, the kernel would reclaim the memory that.
Yeah, so I want to be able to temporarily, right? Now this is different from revoking, right? Revoking means I'm going to prevent the process from using that memory ever again. Reclaiming what means is that if I notice that the resource is unused, I'd like to be able to temporarily take it away, use it for something else, and then provide it again when it's needed, right? This is similar to sort of the process of making a context switch with the CPU, right? And revoking is kind of like the, exiting, right? So I should be able to stop a process from using memory, period, right? Once I've, if I deallocate the memory from the process, you maybe make sure. And this is sort of similar to enforcing, right? But it's the twin of grant, right? Fragmentation. How would I be able to tell that fragmentation has occurred? What specific thing happens that allows me to say I'm experiencing fragmentation?
No contiguous memory.
What's that?
No contiguous memory.
No, what specific thing happens? I don't have fragmentation until I have what?
You have enough available memory, but it's not continuous.
Yeah, but I don't have enough available memory to do what? You're close. What's that? No, that's different. We'll get to a segmentation fault, Dan. This is a property of menu, but again, this doesn't. I don't have fragmentation until I what? What?
Revoke memory from process.
No. Yeah.
There are gaps in the memory which process has.
No, that's what was going to cause this to happen, Natasha.
You request contiguous memory, and the request fails even though there's enough memory available.
Right. I fail a request. right? I fail a request for memory despite the fact that there is enough available memory available. Available memory available. There's enough available memory on the system. And yet I fail a request because the memory is not contiguous, right? What is internal fragmentation? If I'm suffering from internal fragmentation, where is the unused memory? Yeah. Yeah, it's inside my existing allocations, right? And this is usually because I've made these allocations in a way that didn't quite match what the request wanted, right? So the request said, give me 65 bytes of memory, and I gave it 128 bytes of memory, right? And there's reasons to do this, actually. There are allocators that work that way. And you can imagine that it might be more efficient to do this in certain cases. But in that case, what I have is I have an unused 63 bytes of memory that's inside that allocation. Right? That allocation is not going to use that memory, and yet I cannot allocate it to another request. What about external fragmentation? Based on the answers to the previous question, people seem to be more familiar with this. Yeah.
Unused memory between processes.
Between processes? Yeah, you were doing so well to the last word. Right? Would you like to revise the last word of your answer? Unused memory between?
Two processes.
Two processes? It was already plural. Yeah, he's doubling down on the process thing. Unused memory between allocations, right? I have two allocations, and there's, let's say that I have two allocations, and there's 8 bytes in between them, and other two allocations, and there's 8 bytes, and I get a request for 12 bytes. I have 16 bytes available, but not in one piece, right? So the address space abstraction, right? What were we going to do, right? We talked about all these problems with physical allocation, a lot of them having to do with fragmentation. And the goal of the virtual memory address space abstraction was what?
To make all processes have like the same view of memory?
Yeah, we're going to give them an identical view of memory, right? And we're going to make it look like the process has a lot. Right? And by a lot, I mean a really large amount, right? More than the machine has, right? That memory is completely contiguous. There's no gaps in it, right? A completely large contiguous address space. That memory is uniform, and it's private to the process, right? The process, without doing something explicit to share memory between processes, the process has a completely private view of this address space, right? All right, back to the segmentation fault. What generates the segmentation fault, and why don't I load code at the very beginning of the address space? Yeah, Chris.
Segmentation fault is generated when you try to access the memory of another process, or another allocation, so the memory that's been allocated to another process. And don't load everything to the bottom of the address space so that you have a buffer in case something tries to access it, and you don't end up messing up some of the process.
I like the second part of that answer better than the first part, right? So what is the segmentation fault, more generally? Yeah.
You try to access memory space 0x0 to 0x.
Nope. A segmentation fault is much more general than that, Mac.
Accessing memory outside of your allocation.
Yeah, I mean, essentially, a segmentation fault occurs when the process accesses memory that it has not been granted the ability to use, right? A segmentation fault can happen anywhere in your address space, actually. Where do most segmentation faults happen? And what's the reason that I don't load stuff at the very bottom of the address space? What causes most segmentation faults? Dan? Null pointers, right? So I have a null pointer, and then I try to dereference that structure, right? Do most null pointer exceptions go to the address 0x0, true or false? True. Anyone want to argue for false? Yeah, Doug, why?
Because it would be virtual address 0x0, it isn't a literal address 0x0.
No, that's not the reason. Yeah.
Because you're going to get the error when you try to dereference something.
Right, and what is C going to do when I try to dereference something? Let's say I'm using a structure and I try to get like the third or fourth element of it. What address is actually going to cause the null pointer exception? Yeah, it'd be like 12, right? The pointer is 0, but remember, C does this sort of internal pointer arithmetic for you. So you end up with these things like 20, right, or 40 or whatever, depending on the structure you're using, right? Some things go to 0, right? But in general, you see these small addresses. And if you guys are running your kernel and you see this sort of thing, now on your, and this is a little OS 161 trivia question, on your kernel, where do the null pointer exceptions go? They don't go to 0, actually. What's that? No, they don't go to deadbeef.
your exception handlers?
Yeah, where are those loaded though? What's the equivalent for your OS/161 kernel of 0? OX 80 million. Come on, guys. Yeah. Everyone knows that.
Of course.
Or OX 800, then I keep forget, right? So I say OX 80 million, and actually I think it's 80 million. So yeah, so the kernel that you're using, that's 0, right? And so if you see small addresses down there, that's your problem.
So
yeah.
what happens if you like try to dereference a null pointer where the offset is so great that it's into like the static region?
Well, then you get some bogus value.
So you don't get a null
Yeah.
fault.
No, I mean, the kernel doesn't know what you're trying to do, right?
Yeah.
So again, that's why we leave a large gap between the bottom of the address space and the code, right? Your address space is so big that lost memory isn't that big of a deal. And it means you can catch pretty large null pointer exceptions. But yeah, I mean, if you take a null pointer and add like a huge offset to it, who knows what you'll get, you know? Try it and see what happens. Just to get some value, right? You'll get like, if you try to write to it, you might still get a segmentation fault because the code part of your address space might be marked as read-only, right? If you try to read from it, you might get some byte of your code. Who knows what it is? All right, any other questions about address spaces? Kind of a nice idea, and the question is, can we build this thing, right? So fundamentally, what do we need to do, right? And some people have already figured this out. We need to do some kind of address translation, right? Because now we have addresses that don't mean anything anymore outside of a process context, right? And this is very important to remember. A virtual address is meaningless, right? It means nothing outside of the context in which you can translate it, right? And that's a process. If you give someone a virtual address, that virtual address does not refer to any memory. It can't, unless you tell them, here's the process that's going to translate that virtual address, right? Because all sorts of processes are going to be sharing very similar virtual addresses that are going to point all over the place on the machine. They may not even point to memory. We'll talk about that later today. We want to make sure that we can implement this protection scheme as well, right? So again, in order to provide uniformity, we need to do address translation. In order to make sure that the memory is private, we need some way of doing protection, right? And there's an interesting memory management challenge that we've created for ourselves, right? We've given, so one way of dealing with, especially, I mean, now machines have a lot of memory, right? But back in the days of yore, they didn't have as much memory. But here you are, you're giving, like, your machine, on your OS/161 kernel, you're giving processes a 2 GB address space on a machine that has 2 MB of memory, right? Why isn't that a terrible idea, right? You're kind of encouraging, hey, check it out. I got 2 GB of memory. Process like, sweet, I'm going to use it all, right? We don't have that much. So, this is interesting. The other thing that's going to happen, right, so when we look, remember before when we looked at the address space abstraction, it's very sparse, right? That's the other thing that starts to happen. And so we're going to start with this today, and we're talking about this through spring break and probably a little bit after as well, right? How to get this to work. But this is really all we're going to talk about with memory management is figuring out how to get the address space abstraction to work, right? And how to implement it efficiently so that it's fast as well. Because obviously, if we can't provide this efficiently, there's no point in doing it, right? OK, so obviously, we have to break this direct connection between memory address and physical memory, meaning that we're essentially introducing a level of indirection, OK? And when this came up before, I talked about how this is kind of a classic systems technique, right? And it comes up in a variety of different places. Where have we seen this before? This may be fresh in your mind if you're working on assignment 2, and I pray to God you're working on assignment 2. Yeah, so file handles, right? You remember, rather than giving processes direct references to file objects, we created this second level of indirection, right? Where I translate a file descriptor to a file handle, and that file handle contains itself a pointer to the file object. Why did we do this with file handles? What was the reason? It's a specific type of thing we were trying to accomplish. Yeah. Additional security? Not really, actually. I was doing the opposite of protecting. What was I doing? Yeah. Yeah.
I don't know.
You don't know? OK. You were looking like you knew. That was hopeful. Yeah. Sean. Right. So I actually did this so that I could share state, right? So that I could divide my state into a portion that was maintained entirely by the file system level, a portion that was entirely private to each process, and then parts that were actually shared in certain situations, right? And I did that to enable a certain specific kind of IPC, right? But the process of introducing a level of indirection actually is a lot more powerful than that, right? And I want to show you a couple of different ways that we can use this, right? The first way we can use this is that by forcing processes to translate a reference, right? Keep in mind, again, the virtual addresses that I'm handing out to processes are meaningless, right? Without the kernel's willingness to translate them. So the first thing this gives me is a great deal of control, right? If I decide to prevent a process from using that memory, the way I do this, the way I implement this, is simply by refusing to translate that reference anymore, right? I can share things, right? I can give two processes references to the same object. This is kind of what I was doing with file handles, which is kind of a nice property. I can move things around, right? And this is going to be something that's going to be particularly important when we start talking about memory, right? It gives me the ability to alter what the reference sort of refers to, right? And to take the content of the reference and put it somewhere else, right? And then maybe bring it back when I need it. I thought I had another element. And I can also change the thing that the reference refers to, right? And this doesn't actually really come up in virtual memory, but it is something that you can do with references, right? If I want to alter the object, I want to change what's behind it, I can do that. The reference remains the same, right? Now, when we start talking about memory and how we're going to introduce this level of indirection, it's important to at least identify what the memory interface is, right? You know, and this is kind of a weird question. I don't think most people are. How many people have directly used the memory interface in their code? Nobody, right? But what is it, right? It has an interface, like any other part of the system. What is the memory interface? Yeah, Gabriel. It's not the address. The address is provided to the interface. But remember, the interface is supposed to describe what this particular thing does. James.
Malloc and free?
Yeah, Malloc and free is the C library malloc interface. We're getting closer, right? The underlying memory interface, yeah.
Is it similar to vnode?
Is it similar to a vnode? Kind of. It supports a much, much smaller. This is a very, very low-level interface, right? The reason that you don't think about it having an interface is that you don't use it directly. It does have an interface. What are there's two commands in the interface, right? What are they? Copy in and copy out. Yeah, we're getting closer. Load, store. This wasn't meant to be hard, right? Oh, it's fullness memory, right? But yeah, I mean, this is the memory interface, right? And this interface is used by the code you write, not directly, but the C compiler will generate the calls required to access memory in this way, right? And this is usually, you know, if you look at if you deassemble your binaries, you find plenty of these addresses, right? This is how C programs use memory, right? This is how the processor accesses memory. And I don't know, I don't need to go through this, but this is pretty straightforward, right? We've been talking about virtual addresses, right? And just let me make sure that that we make this distinction clear, right? So, because a virtual address is a little bit broader than most of you guys have probably conceived it as, right? So a physical address, when we talk about a physical address on the machine, a physical address is a meaningful number that refers to some byte of actual physical memory, right? A virtual address, on the other hand, you can think of as pointing to something that obeys the memory interface, right? A virtual address is something you can provide to something that is going to obey the memory interface. Basically, it's a reference that you can pass to load and store, right? And it turns out that we can actually put a lot of different things behind that same load and store interface, right? Including things that are not actually technically or in any way memory, right? And virtual address when compared to physical address have a lot richer semantics, right? And the reason they do is because we've introduced this level of indirection. A physical address will always refer to that byte of memory. A virtual address, who knows what it could refer to, right? What it refers to is up to the kernel and the sort of agreement you've made with the kernel about what it points to, okay? So what could be behind a virtual address? When I actually do a load or store to that virtual address, where could that data go to or come from? There's a very low-hanging fruit answer to this question that someone is going to get right away. Hopefully. Doug?
An I/O device?
Oh, no. Yeah, that's actually true, but that wasn't. Come on, obviously, a virtual address could actually point to what? To memory, yeah, of course. Duh, okay? So that's pretty straightforward, all right? But yeah, Doug got ahead of us. But this is an interesting thing. So the kernel may have moved this to the disk, right? And we'll come back to this as a whole. This is one of the things that's so fun about virtual memory, is we get to play all sorts of games now with these addresses, right? So the point is it has to look like memory, and we'll talk about what that means in a minute. It has to sort of obey the permanence that we expect from memory, but it may not be in memory, right? It could be on disk. Has anyone ever used the mmap system call before? You guys are missing out, man. This is great. Yeah, so the virtual address can actually be configured to point to a particular byte on the disk. And that's kind of cool, right? Because what it allows you to do is to take a part of a file and access it as if it were memory, right? So you have some cool data structure that you actually want to freeze into a file. You set up the memory to point to the file. You manipulate your data structure in what looks like memory. And in the background, the kernel is actually making those bytes of memory appear in the file, the exact same offset. It's pretty cool. But the kernel may be caching these addresses. I said that really loud. Sorry, wow. It's like ringing in my ears. The kernel may be caching them in memory, right? It could be somewhere else, in some nebulous place out in the internet, right? I could set up my virtual address to point to like some memory address on another machine, right? It could be in certain types of machine architectures, it might be memory that's on another node as part of the same machine, right? You have memory architectures where the memory that's used, the memory that you see on a particular processor is actually non-uniform, right? Some of it is right nearby, some of it is farther away, right? And it actually might have latencies that are determined by how far your memory request actually has to be routed across the machine to reach the byte of memory that it actually refers to, right? And finally, Doug's address, a port on a hardware device, right? And this is a classic OS technique for trying to make devices look like memory, right? It's a nice way of doing sort of memory mapped device accesses. And there's a portion of the memory that's on your own system that's set up this way, right? It's a nice way of communicating with devices. So with respect to permanence, right? So this is part of our expectations about memory, right? What do we expect about the permanence of memory? Oh. He has no idea. He's like the permanence of memory, right? Oh. No, I mean, we expect it to be transient, right? I mean, when the machine is powered down, you don't expect the memory contents to be the same when you power it up again, right? You don't expect them to change unpredictably unless the machine actually shuts off, right? But while the machine is running, you expect them to be there, as opposed to disk, where we expect the values to be stored permanently, right? So here's an interesting question. What if I'm using virtual addresses and I'm pointing it at a port at a device, right? So let me try to make this more concrete. In order to communicate, like say I have a disk controller, right? And the disk controller needs me to tell it, for example, what byte on the disk I want it to read or to communicate with it in some way over some protocol that we've agreed on, right? I can set up memory. I can set up my memory controller to route load stores to a particular address to that device, right? So now, rather than like using some sort of weird ioctl or whatever, I can just write into the memory address, and the memory controller will take care of making sure those bytes get to the memory, to the disk controller, right? But what about when I'm doing loads from a disk controller? Let's say I have a disk controller that has a port on it that tells me, I don't know, how many bytes of data it's read total. How might that byte of memory, something that the system is going to look like memory, not behave in the way that we would normally expect memory to behave? What do I normally expect memory. In order for it to take a certain value, what do I have to do? Change it, right? I have to actually do a store to a particular byte of memory before I can do a load. When I'm pointing memory at a hardware device, that assumption starts to fall down, right? Hardware can change its ports to whatever it wants, right? So there's a disconnect between, the usual interface of memory, and you see that in how these addresses are cached, right? All right, so something else I can do with virtual addresses, and you see this on your own machines, is that I can set them up so that there's ranges of virtual address that are only accessible when I'm running in the kernel. So when I have the kernel privilege bit set, I can access them. If not, that access will cause an exception that will usually kill the process, right? On your OS 161 system, there's a whole half of the 32-bit addressing range that's reserved for the kernel, right? Virtual addresses can also be assigned the permissions that we're used to associating with files. So, for example, I can set up a particular range of addresses or a specific set of addresses so that they can be read-only. Where would I probably do that? Or what may be one place in my address space where I would set up a portion of the addresses to be read-only? What's that? Yeah, the code section, right? And unless you're writing self-modifying code, right? Which actually is a thing, but I think people haven't written seriously for a long time, right? But if you want to write your own self-modifying code, which again I guess can be really cool, you got to set the code segment to be writable. Otherwise, you can't modify it. And also, as the processor is running on some architectures, I can set up a certain part of memory so that the processor is allowed to load instructions from that memory and execute, right? So remember, now we go back to exec, right? So where do virtual addresses come from? How do I set them up? And specifically, how do I set up ones that point to memory, right? So exec essentially sets up, has this blueprint, and it loads. It does two things, right? First of all, the exec binary actually contains the contents of memory, right? So remember, the exec binary has all the data that's going to be loaded into specific parts of memory, and it also has metadata telling the kernel where to put it, right? So it's a blueprint for how the address space should be created and set up right after exec, right? There's usually code in there. There's usually some data, right, that might be marked read-only or read-write, but not executable. And then the heap is usually initialized at this time too, even though it might be empty, right? And then when the process starts to run, I'm going to set up the stack, right? This is done during exec, right? It's not from the ELF file, but the stack is set up, and this is something that you guys get to do for assignment 2, right? So the stack has, the arguments that are passed into exec, and then is used by the first thread as it starts to run, right? So going back to PMAP, right? We looked at this before, just to refresh your memory. PMAP shows you the address regions that have been set up for a particular running process. Kind of a neat tool. So this essentially what this is saying, right? We go back to granting and enforcing allocations. These are all the addresses that this particular process is allowed to use. And I've clipped up some things here, right? But so let me see here. So what would happen if I tried to access the byte of memory right before this one? What would that trigger? A segmentation fault, right? Because the kernel has not been set up to allow the process to use that byte of memory, right? These, this stuff in here probably came out of the ELF file. This is stuff that was loaded at runtime through a dynamically loaded library, which is not something we're going to talk about. And then this area is a portion of the address space that was set up for the kernel's, sorry, not the kernel stack, the thread stack, right? And any accesses outside of these regions will cause a segmentation fault. And you can see as well that there's a huge, I think the heap is probably started here and growing this way. And there's a pretty large range of addresses between the top of the code and where the libraries are being loaded, right? So that's area that the process can dynamically allocate using malloc, right? Why? So what's as you guys have started assignment 2, you probably started to learn a little bit about memory layout on the MIPS architecture. What's a big difference about this process memory layout from the ones that you guys are used to? Where do your process address spaces stop? Where do the kernel addresses start? Does anybody know? So remember OX 80 million, our old friend, right? So OX 80 million is the boundary point. We'll get to this in a minute, between the user addresses and the kernel addresses on the MIPS architecture. Here, this is Linux, right? And you can see that the user address space is going all the way up to almost like OXC million, right? Or C0 million, or however you say that in hex, right? Why is that? Why is Linux giving this process a larger address space? Why would systems today want to try to give processes larger address spaces? Yeah, so keep in mind, on these old 32-bit machines, what's the largest amount of address space I can give a single process? 4 gigabytes. How many people have more than 4 gigabytes of RAM on one of their machines? The rest of you guys should get with this, man. It's awesome. But it does raise this problem, which is that I have 12 gigabytes of memory on my machine, and now the most I can give to one process is 4 GB, right? That seems a little unfortunate, right? When this whole thing got going, we were talking about machines that had like 4 megabytes of memory. So gigabytes seemed huge. Now my address space might not be even large enough to allow the process to address all the memory on the machine. And there's a whole bunch of gross, nasty hacks that a variety of machines use to solve this problem. And the long-term solution is probably just wider addresses, which is where most systems are going, right? With 64-bit addresses, it's like I can address like every atom in the universe or something. Like it's excessive, right? It's certainly more than the amount of memory that you're going to have on a machine, right? So another place when we start thinking about where virtual addresses actually get allocated, right? So exec is one place, right? Fork is another. So fork, as we remember, just copies the address space. So the child process ends up with an address space that looks identical to the parent, right? And that includes the heap. That includes one stack here for the thread that called fork. Potentially, depending on how you handle this, you might have other stacks, but maybe not. And then all the code and any sort of static variables that the parent had when it called fork, right? And here's a case where the child has the same virtual addresses, right? Does everyone agree with me that the address space is identical, right? So the virtual addresses available to the child are the same, but the physical addresses had better be different, right? So if I call fork, right? You can run this code, and these two, right, will print the same address. Well, I just gave away the reveal, I guess, right? So after fork, the parent and the child both have an integer I as a local variable that's available to them, and it prints off somewhere. I made this address up, right? But whatever, it's going to be somewhere. It's going to be the same. What will the value of I be in the child at this line? What had it better be? What's that? It better be 3, right? Despite the fact that the parent has set it to 4, right? The child, despite the fact it's using the same virtual addresses, has those virtual addresses pointed to a different piece of physical memory, right? So this is kind of the easiest way to convince yourself that these virtual addresses mean nothing outside of the context of a process, right? If you said here, oh, what's at value OX, 20,010, you don't know, right? You need a process ID to complete that translation. And we talked about fork, and we talked, back in the early days of the class, we were talking about fork. We mentioned that copying all this memory is really expensive, and it's really dumb because the first thing that a lot of processes do after calling fork is call exec. And at some point, we're going to talk about how we work around this in the memory management layer, and it's cool, and it uses these same set of translation tricks that we're going to talk about. Right? So The third way that we create virtual addresses is through the sbreak system call. How many people have ever used sbreak before? Yeah, again, good, right? Who knows who normally calls sbreak? A lot of you guys have generated calls to sbreak before. You just didn't know that you did it. Who generated the call to, who called sbreak on your behalf? Yeah. GDB? No, not GDB. What's that? Malloc. That's right. How many people have used Malloc? OK, so you've all used sbreak, right? Malloc didn't tell you it was doing it, but Malloc called sbreak, right? Because the only way Malloc gets memory from the kernel, right, is to call sbreak. Sbreak asks the kernel to essentially move the breakpoint, right? So if this is where the heap was, and the heap is full, Malloc has allocated all of the memory in the heap, or there's too much internal fragmentation or external fragmentation, and Malloc can't satisfy your request, it makes the heap bigger, and it makes the borders surrounding the heap thicker. Right? That's important to do at that point. Right? You need more protection for a larger heap from the white space. So this is essentially what Malloc does. And it probably wouldn't grow that much all at once, right? But you ask for a certain amount of memory in Malloc. When it runs out, so Malloc manages this sort of memory internally. And we'll talk a little bit. I don't know if we talk about allocators or not. Allocators are cool. I don't know if I cover them. Maybe I do later. But anyway, when Malloc runs out of memory internally, the way it asks the kernel for more virtual memory is by calling sbreak, right? All right, so the fourth place that I think is, again, just sort of worth mentioning that virtual addresses can get created, because this is pretty neat, is mmap, right? So mmap is a system call, and it creates virtual addresses that map to a file, right? Oh, I didn't have anything much more to say about mmap, right? But mmap's cool, right? And mmap, again, allows you to manipulate a file as if it were memory. And in many cases, databases do this a lot, right? Because databases have big sort of complex data structures and then files underneath them, right? And so databases frequently use mmap to map huge regions of files, right? So that they can manipulate data structures internally as if they were memory, right? It also gives you a little bit of nice caching, because the operating system will cache this data as if it's a file, right? All right, so on each machine, and I don't want to go too far down this particular rabbit hole, because this is one of those cases. It's like boot, right? Like every machine is sort of its own private universe. But different architectures have different ways that they lay out the memory space, the physical memory space, right? And what you really need to know, particularly for assignment 3, is how the OS 161 system emulates the 32-bit MIPS architecture, right? So it's a 32-bit architecture, right? So my addresses are 32 bits wide. That means they start at 0x0 and they go up to 0xFF million, or whatever that is, right? Does anyone know this? Is there like hex speak? Is there like a way to like say hex addresses like correctly? You guys aren't dorky enough to answer this question, I guess. I'm sure there is. I'm sure you can go online. There's probably some YouTube video where someone will like train you on how to say hex addresses, right? But anyway, I've never seen it, so I don't know. But it's just a bunch of Fs, and there's 8 of them. And so the MIPS architecture, and now when we're talking about architecture, we're talking about hardware, right? This is something that the kernel has to deal with. This is the memory controller itself that implements this. The kernel has no control over it, right? And the MIPS architecture defines 4 address regions. Remember, this is an old system, right? And so at the time, setting up 2 gigabytes for processed virtual addresses was probably seen to be an enormous amount, right? A 2 gigabyte address space, wow, thank you, kernel. Like, all this memory just for me on a 2 megabyte machine. So that was the thinking at the time, right? This memory is accessible by user processes, and it's translated according to how the kernel sets up these mappings, right? So this gets a little bit weird, right? Because every process has these addresses, but they're all virtual addresses, right? So anytime an address within this range is accessed on the machine, it will be translated by hardware according to rules that the kernel is going to establish. So are you resting your hand? Or?
No, I'm just curious. Is
Yeah.
it 2 gigabytes per 4, and that's why it's 4?
So remember, these are this is how we're dealing up the virtual address space, right? So this isn't. So this is going to be, OK, that's a good question, right. So this is translated differently depending on which core you're running, right? Every core, you got a little bit ahead of me. Every core has built-in hardware that's going to help us translate these addresses, and that hardware is separate, right? So, and that's important, right? Because I could have two different processes running on different cores, accessing this range of memory at the same time, and I need those mappings to be true. Right? That's a good question. So the next part of memory I have is what's called kernel direct mapped addresses, right? Everything above 0x80 million are kernel addresses. If I try to access them when I'm running in user mode without kernel privilege, that will generate an exception and it will trap into the kernel. These are what are called direct mapped, right? And what that means is that they're translated in a very, very simple way. The way they're translated, and this is done by hardware, this is hardwired into hardware, there's no way to change this, is that the hardware simply subtracts 0x80 million, right? It just lops off a bit. And then it uses that to try to access a byte of physical memory, okay? So again, when you talk about virtual memory, we usually talk about being able to configure how virtual addresses are translated. This area is not configurable, right? If you translate 0x80 million, it will translate to what byte of physical memory? 0, right? Yeah?
Why on the PMAP slide then did the addresses start at 80 million?
They didn't. They started at 8 million.
Oh, 8.
Yeah. 0x08 million.
Okay.
Yeah. I wouldn't do that to it. I'd probably put the 0 there, right? Otherwise, you can't count, right? Every 32-bit hex address should have 8 digits in it, right? Yeah, that was the beginning of the code, so that was very, very early in the address space. Good question. And the other thing to keep in mind is that this part of memory is cached, meaning that each processor will actually do caching close to the core, like what you guys are familiar with is like an L1 or an L2 cache, right? So this next set of addresses is also direct mapped. It's only accessible to the kernel. It's half a gigabyte, and it's uncached. Can anyone guess what goes in here? Why wouldn't I not cache these memory addresses? So if I cache an address, it means I'm stashing a copy locally to manipulate it, which is nice. But what particular use of memory that we discussed before would actually make this very dangerous to do? Yeah, Chris.
If it's the actual operating system, would you really need to write to it?
No, I could still cache that code. So that code actually probably lives in here, right? Yeah. Yeah, and in particular, so remember, this is MIPS 32-bit, so this is like I don't know when MIPS, in 80s, maybe? So, I don't know, maybe there's an internet, maybe not, right? But what sort of outside change would this be subject to, right? This probably isn't NUMA, it's probably not mapping to some internet port, but what could be behind it that could change, yeah?
It could be multiple threads from the access in one copy of the variable.
No, I could still cache that, if I'm careful about how my cache coherency protocol, yeah. What's that? Yeah, so this is where devices live, right? And I don't cache the value because the device can change the value at any time. And if I try to cache it, I might cache a stale value and it might change behind the scenes, right? One of the reasons caches work is that they assume that they can see all the changes to memory, right? But if the hardware is changing the memory, quote unquote, behind my back, then the cache isn't going to work, right? And finally, so again, all of these addresses are translated by the memory bus itself, right? In this case, they're just translated by subtracting 0x80 million for that top area. For the second area, the hardware, there's going to be some hardware-specific way to map that to a port on some device. Up here at the top gigabyte are kernel virtual addresses, right? So this is very similar to process virtual addresses. These are translated, meaning that they don't refer to actual physical memory, but they're only accessible in the kernel. And there are things that you could do with these kernel virtual addresses. At least for assignment 3, we encourage you not to try, because this can create some complications, right? But the kernel can essentially use these in very much the same way that users use virtual addresses, right? All right, so let's just put this up on the screen. That's my direct map cached area. I've got kernel virtual addresses, and then the direct mapped uncached. So you guys will see this again, probably in recitations for assignment 3. Any questions about the MIPS memory map? Yes. And again, every device has its own way of doing this. Right? Every device will come with a particular memory layout. And one of the things that kernels are forced to do during boot is figure out how the device maps memory. Right? You got your new box from Newegg. You ripped it open. You shut your machine down. You put 2 more gigabytes of RAM in there, and you booted it up. And somehow the kernel found it. Right? That's pretty neat, right? I mean, it's kind of cool that that actually works. But there's a process during boot where the kernel and the system have to sort of cooperate so that the system could tell the kernel, hey, there's this new 2 gigabytes of memory, and here's how you access it, right? Here are the addresses, the physical addresses that you can use to refer to this, right? All right. So when we talk about translating addresses, this is one of those fun cases where there's this nice cooperation between hardware and software. And we'll talk a lot more about this next week, maybe starting Friday. But both hardware and software are involved. So one of the challenges we're going to have is making this translation fast. We haven't talked about how to do that, right? But clearly, so for example, one way I could do this is every time a process wanted to access a byte of memory, it could like make a system call, essentially, right? Tell the kernel, load at this address, right? And the kernel could like figure out where it was and do that. How terrible would that be, right? That would be bad. That'd be really bad, right? Like memory's supposed to be fast, remember? It was supposed to be like faster than disk and stuff like that. And now every time I change a byte of memory, I have to like use the kernel to do it for me. So that's terrible. So we need some help from hardware. I'm going to talk about how this works. But the hardware is the mechanism here, right? And we want to make sure that the OS has a firm grip on policy, because the policies determine the operating system's ability to do all those nice things with virtual memory that we wanted to do before. Grant it, revoke it, move it around, right? So this is another nice case where the hardware exposes some features to the operating system that allow the operating system to tell it how to translate addresses, and then we use the hardware to make this translation fast. And again, what we want to do is essentially allow the operating system to tell the hardware what to do, and then the hardware goes along and does it rapidly without involving us anymore. All right, so on Friday, we'll talk about different ways to translate addresses, different approaches to sort of mapping from a virtual address to a physical address, and the implications these have in hardware for making this process extremely fast.